First of all, I just want to thank Hassie. That was a fantastic talk. I could have spent the next hour asking questions about it, and I'll try and do that at some point during the rest of the meeting. I hope he's staying around for the rest of the time. It was brilliant. Thank you so much. It's a fascinating field, one of those rare occasions where something completely new turns up in the biology of aging, completely out of left field, and everyone gets fascinated by it. So I'm really pleased that we were able to have him here to give our keynote. And I'm just as pleased to have this panel here. These are, of course, a trio of fantastic leaders in the field of the biology of aging and regenerative medicine. And we're going to hear a lot of what they're doing over the next while. I think that the three of them form quite a nice spectrum, actually. I think there's a great deal of work that you'll hear individually from each of them. This is the kind of thing that I've always liked to do in the conferences that I started running back in 2003, as you heard at the beginning of the session, to bring people together who don't normally sit in the same conference, let alone in the same session of the same conference. And so we'll hear a bit of that today. But I'm going to start out in my somewhat traditional characteristic style by being a bit provocative and saying what I think is the main purpose of this meeting. We've heard earlier, and I absolutely want to emphasize, that this is all about bringing collaborations together, bringing people who start out from different spaces, different mindsets perhaps, different ways of thinking, to work together, to synergize, to solve the world's biggest problem, the problem of age-related ill health. And we need more of that. The fact that this conference is not happening in the, at Wembley or at Madison Square Gardens, it tells us that people haven't really got the message enough yet. But it also, putting it positively, tells us that the people who are in this room are at the coalface, the cutting edge of a movement that is going to take over the world. So everybody here should feel proud to be part of the early stage of what will be the biggest revolution in the history of humanity. All right, so let me set the stage. And most of what I'm going to say is going to be, if you like, a story of the progression of thinking in the whole concept of what we might do about this terrible thing called aging. And I'm going to, obviously, since I'm only going to speak for 10 minutes, I'm going to be very brief and perhaps a little bit overly brief in some ways, but I hope that's going to be okay. First of all, one thing that struck me when I first started in this field was that if you asked people what aging was, everybody would give a different answer. Even people who had been in the field and were studying the biology of aging for 30 years, they would give different answers. And that struck me as a drawback. So I always like to be clear when I talk about aging at the outset about what I think the definition of aging is. And I have crystallized that definition progressively over the years. This is the definition that I like now. I like to start by emphasizing that aging is not actually a phenomenon of biology at all. It's a phenomenon of physics. It's something that's going to happen to any machine that has moving parts. Machines that have moving parts, simply by the second law of thermodynamics, irrespective of the fact that, of course, machines, whether living or not living, are open systems, aging is going to consist of the creation of damage, because damage is going to be something that machines generate as a consequence, as a side effect of their normal operation. And that damage is going to accumulate, and the machine will be able to tolerate a certain amount of it without significant impairment of function, but eventually the function will be impaired, and that is that. So it's not something to do with life. And I mention that because it's going to be rather important later on in what I have to say. When we do think about biology, however, we can use terminology that's familiar to biologists. We can talk about words like metabolism and pathology. And I think, we can just summarize what I just said on the previous slide in these 3 words. Metabolism causes damage throughout life, and damage is kind of, I haven't defined the word damage, but we can define it as the thing that is the intermediate between metabolism and pathology. In other words, the things that progressively change in the structure and composition of the body over time, and that eventually contribute to decline in function. So this is all that aging is, and that's quite useful. So then we have to ask, what can we do about it? Obviously, what we want to do is attenuate this chain of events. We want to try and diminish, or ideally eliminate, the linkage, the causal chain that starts with metabolism and ends with pathology. And the first thing that people thought about, and if you like, the first way in which the attempt to do something about aging lost its way, was that we made this fantastically important mistake. And when I say we here, I don't just mean scientists, I mean absolutely everybody. Today, as of today, if you ask pretty much anybody to describe in some kind of classification way what types of way can you get sick, they will say something like what you see on this slide. They will say, well, let's see, there's communicable diseases, infections, and then there's congenital diseases, things that we inherit from our parents if we're unlucky. And then there's the chronic progressive diseases that we mainly see in old age. And then there's this fourth thing out in the stratosphere called aging itself, which consists of this kind of collection of non-specific, rather nebulous phenomena like sarcopenia, the loss of muscle mass as you get old. And people intuitively think of this column 4 as completely different, so different from the other columns that they have doubts as to whether it's even in principle amenable to medical intervention. And of course that means that it becomes difficult to think about it as something we should agitate for medical intervention for. And so I feel that this is a fundamental, really profound and powerful reason why there is still so little money in biomedical gerontology. This, of course, is the correct answer. All the columns are the same, but the big black line is in a different place. Column 3 is fundamentally indistinguishable, other than terminologically, from column 4, whereas it's completely different from column 1. Column 1 being things that are external and that come from outside and therefore can be eliminated from the body, and you won't suffer them again unless you get reinfected. Things that are side effects of being alive in the first place are not like that. And column 3 is all about being a side effect of being alive in the first place. These are things that wouldn't happen to you until old age, just like column 4. Once we get that straight, things get a lot easier. But if we don't get it straight, this is what happens. Geriatric medicine. Now, I'm not saying geriatric medicine is useless, and I'll come back to that later on. But I am saying that it's never, ever going to solve the fundamental problem of age-related ill health, because ultimately it's trying to treat column 3 like column 1. It's all about trying to address the pathologies of old age as if they were infections, which clearly can't work because the damage which is driving those pathologies is continuing to accumulate. So the geriatric medicine is absolutely certain to become progressively less effective as time goes on. Now, I am not, of course, the first person to point this out. That actually, this is not the only reason. You're not supposed to be able to read this slide, don't worry. Everyone says, well, geriatric medicine doesn't work very well because it's really complicated. There's so much that goes wrong at more or less the same time, and they interact with each other. And of course, that's part of the reason why it's really hard to deal with aging. But the fundamental reason for why geriatric medicine is a non-starter is because it's conceptually wrong, as I just explained. So as I say, I'm not the first person to have said this. Perhaps a century ago, a few people started to work out that actually, no, we need to be more preventative. We need to somehow stop the damage from getting to the pathogenic threshold in the first place. And in the early 20th century and since then, the idea was to capitalize on what we saw in nature, on the fact that some species seem to age a lot more slowly than others, and maybe we can figure out why, and maybe we can use that knowledge to generate ideas for therapies. Great idea. Hasn't worked at all. In fact, it worked so badly that by the 1970s and 1980s, it was positively verboten within gerontology to even talk, at least in a grant application or on camera or anything, about the idea that we might actually do anything about aging ever. And this is, of course, why. Metabolism is just as complicated as aging, if not more so. Those of you who write software will understand that this is the ultimate catastrophe of, uncommented spaghetti code. And And you're just not going to be able to mess with it in a manner that actually stops it from doing the thing you don't want it to do, the creation of damage, without at the same time having unintended consequences that do more harm than good. But all of that changed, of course, about 25 years ago, as we all know, when people suddenly started to think hard and find that it was possible to mess with metabolism in a clever way, in a way that essentially exploited what evolution has built for us. If you have a really complicated system that does a really complicated thing you don't want it to do, you're just not going to be able to stop it doing it by simple means. It's going to be complicated, unless the complicated system has this bizarre kind of sleeping ghost in the machine that can be activated, that is normally sitting there inactive, but can, in principle, be activated to suddenly have the change, the complicated change. Of course, the ghost itself has to be really complicated, but you don't need to know that if the thing that turns it on is simple. And of course, that's exactly what calorie restriction is. A really simple intervention that was discovered in the 1930s, 80 years ago, if not earlier by some definitions, and which extends lifespan a lot in mice and rats, like 30, 40%. Fantastic. And of course, in the late 80s and early 90s, discoveries were made that have led to a huge transformation of the field of biogerontology. Discoveries that one could effectively emulate calorie restriction by simple genetic interventions, and more recently, of course, by simple pharmacological interventions. We can do this. And that seems like a fantastic piece of good news, sidestepping the whole problem of metabolism being such a mess. Unfortunately, of course, it also hasn't worked. Not really, at least. And this slide is perhaps the one that I was thinking about when I described my talk as going to be controversial. I think that the things I'm writing on this slide are unjustifiably swept under the carpet by far too many gerontologists. We really need to be honest about these facts. In the 1930s, Clive Mackay, who discovered, or at least was the first person to really promote and publicize the life-extending effects of famine, he was able to extend the lifespan of mice and rats by order of 30 or 40%. Pretty much exactly what we can do now. Pretty much exactly the same. That is rather important to remember. We haven't actually made any significant progress since then. Now, of course, that's not to say that we won't. I am always the first person to point out that technology is all about putting two and two together and making 17, and that you don't expect to see progress until you've got all the components working. So this is not a show-stopping objection to the idea, but it's still something that we mustn't forget. The second point also is rather important to remember. The insulin IGF signaling system and other aspects of the fundamentals of the response to calorie restriction are things that are conserved across evolution, even down to yeast. But the consequences, the metabolic and anatomical consequences of those things are not conserved. Rodents don't have a Dower pathway, a way of going into some kind of spore that lets them live 5 times longer than they normally would. They don't have diapause. They have things like hibernation, but not the kind of diapause that fruit flies have, that let them overwinter and live several times longer than they normally would. This kind of thing needs to be taken into account. And when we get a little more analytical and we ask a couple of things about what we can learn from this, I think it gets even scarier. The first thing is, yes, drugs and mutations that we have looked at, they can get to do about as much in a given species as calorie restriction itself does, but no more to speak of. There's one big exception in C. elegans, which we have tried to research, actually, with the help of a very excellent researcher who actually, I'm afraid, is not here today, named Bob Smukler-Rees. Yeah, I think the thing is, we never beat it. We just about never beat it. And of course, this is what you would expect if the only way that calorie restriction itself is working is by turning on some sleeping giant, right? You can only turn on the sleeping giants that are actually there. Finally, and this is the critical thing, the longevity benefit that you get from famine of any kind, whether it's straight starvation, whether it's starvation with optimal nutrition, whether it's some kind of drug or whatever, it's far more impressive in short-lived species, a factor of many, than it is in medium-length species like mice, where you only get 30 or 40 or 50%. And it's more than you get in dogs, and it's more there than you get in monkeys, and so on. So, I mean, like, this is actually a data point that we need to pay attention to. And, see my last sentence? It's blatantly predicted. It's exactly what you would expect if you just take into account the fact that long famines occur in nature less often than short famines. It's really obvious, this stuff, but people sweep it under the carpet, and they really needn't. They really shouldn't. But that is the kind of thing that led me to the third way, so to speak, the maintenance approach, the damage repair approach that, of course, SENS Research Foundation pursues, which says, let's not try to mess around with, let's attenuate that process that metabolism creates damage, and let's also not try to attenuate the process by which damage creates pathology. Let's attenuate the combined process by cutting it in half, by uncoupling the two components of the process, by repairing damage and thereby letting damage be created at the normal rate, but not letting it accumulate to a pathogenic level. Why is that so promising? Well, there are two fundamental reasons. The first reason is that we can come back to what I said earlier about aging being a phenomenon of physics. It works. Preventative maintenance works in actual life, actual real life, with inanimate machines like cars or airplanes or whatever. We have vintage cars that are at least 10 times as old as they were ever designed to last, and we have them because of preventative maintenance, not because of cleaning up their metabolism so that they don't create so much damage, not because of putting the door back on when it falls off, but because of preventative maintenance. Now, the body is far more complex, no question, but how much more complex? And the key question, because of what the maintenance approach is, the key question is not how much more complex is the metabolism of a living organism relative to the metabolism of a car, and it also isn't how much more complicated is the pathology of a living organism to the pathology of a car. The correct question is how much more complicated is the damage than the damage that a car accumulates. And yes, it's definitely more complex, but it's not nearly so much more complex as the other two. The thing that I have been trying to persuade people of for the past decade or so is this, that actually we can think about the damage of aging, which is complex, in a reasonably divisible way. In other words, we can actually compartmentalize it into a manageable number of categories. Here they are, 7 categories on the left-hand side of this table. The utility of that classification is simply that for each category there is a particular way of going about repairing it, going about implementing the maintenance approach. And the comprehensiveness of this classification is, of course, a hypothesis, it's a question, and we have been very honest since the beginning in addressing that question and trying our very best to test that and find ways in which other things might not fit into these categories. But we seem to be getting away with it. And that's good news. The longer this classification stands the test of time, the longer it's likely to continue to stand the test of time. So in closing, I just want to come back to the collaboration aspect. At the beginning in my title, I called this the 4th era of gerontology, but that's kind of a misnomer, because eras are supposed to, succeed each other. And the fact is that's not what's happened here. It's more of a pyramid. If we take the first era, the geriatrics era is alive and well. And that's not a bad thing. The fact that geriatric medicine will never keep us alive for all that much longer than we are already is not a problem, because it can keep us alive with the help of the other phenomena, the other concepts. The reason why geriatric medicine doesn't work is because damage continues to accumulate, but the whole point of the other 3 approaches is to stop damage accumulating, right? Similarly, the approach of whether it's trying to redesign metabolism or whether it's trying to activate sleeping giants, those things may not really work because the sleeping giants aren't there, but they can still augment what we can do with rejuvenation biotechnology. So I think it's critical to understand that we need all 4 of these approaches to be pursued really aggressively. And that's what this conference is about, and that's what the mission of SENS Research Foundation is about. I'll stop there and introduce the rest of the panel. Thanks.